Welcome back. This video is going to cover bagging and random forests, which extend the classification and regression trees that we were talking about in the previous videos. So I think it's kind of interesting to establish the timeline on this. So this is the Jerry Friedman and Leo Breiman proposed classification and regression trees, CART, back in 1984. And about 10 years later, Leo Breiman extended this method with this approach called bagging. And so that's going to be the first method that we discuss today. And then a few years after that, he came up with a method called random forests, which is one of the most cited works in machine learning. So this is a very major and important method. So in order to get us into this, I want to go back to the final slide that I had on trees. And so this was just a summary of the strengths and weaknesses of trees. And what I told you was these trees have a weakness. And the weakness is that they're very high variance, unstable estimates. So on this next page, let me just illustrate this. I was working on a problem for a bank one time. The particular, problem itself is not that important, but I had a data set, and I was regressing some variable on everything else in the data set. And in this example, what I've done is I've drawn two different random samples of size 100. So here I drew a random sample of size 100. Here I drew a different sample of size 100 from the exact same data set. Okay, so what would be desirable is if I used 100 observations from this population, and then I used a different 100 observations from this data set, I'd come to the same conclusions. Well, look at the two trees, and what you'll see is that they're quite different. Now, maybe the predictions that come out of these trees are quite similar, but the trees themselves are very different. And so if I were interpreting some of these things, I might come to very different conclusions because different variables are entering, different splits are happening. And that's a reflection of the criticism I just mentioned. So they're very unstable, they're very sensitive to the particular sample you have. And so this was a well-known problem back in the 80s and early 90s. And Breiman had a very important insight around this, which was that we could take this instability and use it to our advantage. And so here's the idea of bagging. So what we're going to do is draw many samples from the data we have. So we're going to draw a sample of size n with replacement. So I replace an item every time I draw it and put it back in the hat, draw another item, and could be the same item I had a little while ago, but that doesn't matter. Then I go estimate my tree, and I do this many times. So, originally the bagging article talked about maybe 25 times. We're going to see that this number grows when we do some random forests. And then after I've estimated the tree, and I've done this 25 times, I simply average the trees. Okay, so whatever the predicted values are for a regression tree, average them. If it's a classification tree, we'll take a vote. So on a particular training case, if, say 15 of my 25 trees say it's in class A, and 10 of the trees say it's in class B, then I would say class A would win, and I would put it in that class. So that's an incredibly simple but powerful idea. So I'd like to just let Breiman summarize the key properties. I pulled some quotes from his original paper. And so what he has to say is that tests on real and simulated data using CART, as well as variable subset selection. So I also mentioned in my previous video that forward selection, backward selection, all these methods have similar problems with instability. So that these methods show that bagging gives substantial improvements in accuracy. Now, in the original paper, Bryman did some math and established what was necessary in order for bagging, this very simple procedure, to improve things. And the key element is the instability of the prediction methods. So if perturbing the learning set, so perturbing the learning set, meaning drawing a slightly different sample of observations from it, can cause significant changes in the predictor constructed, then bagging can improve accuracy. So if you have a method that's very stable, so let's say you're building a regression model and there isn't a lot of multicollinearity in there, so then bagging is not going to help you. But if you have stepwise regression and say a fair amount of multicollinearity in there, then bagging is going to lead to an improvement. I love the way Bryman summarizes his method, and this was in the discussion section of the original paper. So Bryman says, bagging goes a long way towards making a silk purse out of a sow's ear, especially if the sow's ear is twitchy. So I might need to explain this. This would be an expression that my grandmother would have used. She would say something like, well, you can't make a silk purse out of a sow's ear. And so, a sow is a pig. And so if you start out with very bad leather, it's the ear from the pig, you can't make a beautiful purse out of it. But, Bryman says that's false. You can make a beautiful purse out of ugly leather as long as the sow's ear, the pig's ear, is very twitchy. So that's the instability that he has. So all you have to do is add a loop to the front end that pulls a bootstrap sample. So bootstrap samples where you pull items with replacement. So I pull an item from my data set, I put it back in there, pull another item, and that's how I get a bootstrap sample. And then all you do is estimate the procedure and do some back-end aggregation. What one loses with the tree is a simple and interpretable structure. So remember last time I said one of the benefits of trees was you get this very simple structure that you can explain to normal people. Well, now you have a couple dozen of these trees and you're not going to be able to explain it so simply. But what you get is accuracy. So I want to kind of summarize the main points that you need to know about bagging, and for that matter, random forests, which I really haven't introduced yet, but they're an extension of bagging. So what we're going to see is that bagging is unlikely to overfit the data, even if individual trees overfit. So you can overgrow your individual trees, but as long as you average a bunch of them, it's unlikely to overfit. Another big advantage of bagging in random forests is that they lend themselves to parallel computation. So if you have multiple cores, you can set each one of these cores estimating a different tree model or a different bootstrap sample. Then they all come back and you average the results. A third very important benefit of bagging in random forests is that they enable something called an out of bag. So OOB is the abbreviation estimate of your prediction error. So remember that we've considered the gold standard for evaluating prediction models to be having a test set or k-fold cross-validation. We want some sort of an out of sample estimate of prediction error. And we've also seen how much work it is to get these. If you're going to do 10-fold cross-validation, you got to build your model 10 times and apply it to the test set and all that. But what we're going to see is that using either bagging or random forests, we'll essentially get one of these honest estimates of prediction error for free. Okay, so it's going to come with the procedure. So these are really major contributions to machine learning. Now, let me try to build up some intuition. Bryman does some mathematics to justify why this is a good idea in his original paper, but I'm going to try to kind of give you some insights about this with a simple example. So let's just say I'm going to build 20 trees on my sine wave example. So my sine wave example was go generate 3/4 of a period of a sine wave, add a little bit of random noise to it, and see what happens. All right, so if we look below, this black line is the true sine wave. So that's the truth. That is my true f at x. You're going to see the points out here are, after I've added a little bit of normal air to the sine wave, you get those solid points. Now, I've implemented bagging by hand here. In the future, you're going to use the random forest command to estimate a bagging model, but I think there's some value to us doing it by hand but once. All right, so what I'm going to do is make myself an array to hold the answer. And what we'll then do is have a for loop where I let I range from 1 to the number of bag samples that I want. So in this case, it's going to be 20. This next line identifies the training set. So I'm going to draw a sample from the set 1 through n, so that's just my indices, of size n. And this true means I want to do sampling with replacement. So each one of these samples will be different. If you're interested in seeing an example of this, let me just go over to R for a second and show you one. So let's just try this. I'm going to set my seed. So if you want to try this at home, you can do the same thing. So I'll set it to my favorite value, 1, 2, 3, 4, 5. And if I say sample, let's do 1 through 10. And I'm going to draw a sample of size 10 with replacement. And so you can see, well, it looks like 8 came in 3 times this time, and 1 never made it in. If I repeat this, you're going to see I get a different sample of size 10, and so forth. So that's what the sample command is doing. Now, the next thing we do is we go fit a tree using that training set. Then, just to show what's happening, I'm going to plot the first 6 trees that I get. So this gives me the predicted values. I've added those in blue. So each one of these blue lines gives the fitted values from one of my trees. Now, remember what bagging is all about. We're going to average our estimates. So I'm just going to take answer and set it equal to answer plus whatever the predicted values are. So we run through this loop, say 20 times, and then if I divide answer by 20, I get the average predicted value. Then if I superimpose this, this average on top of my plot, I get, you're going to see I made it red, this big red line. Now, I didn't give myself that much data, so what's going to happen here is it's a fairly hard problem for us because the sample size is not absolutely massive. Well, what you're going to see is that when there's disagreement amongst my estimators, so look up in this region here, look over in this region here, there's a whole lot of disagreement between my individual trees. But when I average all these estimates that disagree, on the average, I get about the right answer. So this red line is kind of hugging the black line, the true black line. Likewise up here, it's not doing too bad of a job. So that's what Bryman was saying. When you've got an unstable estimator, when you average all of them, even if some of these might be overfitting my data, as long as some overfit in one way and some overfit in the other way, the average will be about right. Now, where we have problems is when there is no instability. And so down here, what you're going to see, all the blue lines are on top of each other. They all agree that's where we want to make a split. And the red line breaks down, right? So the red line is substantially less than the black line, indicating the problem with that estimator. So I hope that gives you some intuition why, having a bunch of estimates that are wrong, as long as on the average they're right, is a good thing, provided that some are higher, some are lower than the true function. After the bagging paper was published, there was a lot of work trying to push it even further. And so, by drawing bootstrap samples, we could destabilize our estimator and improve it. What would happen if we destabilized it even more? And so we saw methods like output smearing, where they tried to add noise, random noise, to the dependent variable in each time they fitted a model to destabilize it even further. So in this spirit, I thought I would just show off another example of this, which is kind of counterintuitive to me. And so, ordinarily, we know that larger samples produce more reliable estimators. So the variance of, for example, a sample mean is sigma squared over n. So the larger the sample size, the more reliable our estimate of that mean will be. And it's similar with regression functions. If I have bigger sample sizes, the parameters will be estimated more reliably. Well, if we wanted to destabilize an estimator, we should then reduce the sample size. And so, that was kind of a wild thought, but I thought I would try that on the wave example. So I generate various numbers of training points. So here we have 1,000, here we only have 500, here we have 80, and here we have 20. I then fit a bagged estimate on this. So I estimate a bunch of trees and then apply the fitted result to a test set of size 10,000. And I compute the mean squared error on the test set to give me the result. So what you'll see happening is very consistent with what Bryman said, which is the more unstable your estimate is, the more that bagging will benefit. So what you'll see is if you have a sample of 1,000, the breaks tend to occur at roughly the same places. So you're going to see these blue lines closely follow each other, and the consequence of this is your bagged estimate, the red line, resembles a step function and doesn't fit that well. Our test set mean squared error is 0.0761. Now, if I start reducing the sample size, what we see is there's a little bit more disagreement among my individual tree models, and the red model, the bagged estimate, works a little bit better, as reflected by the test set mean squared error, so it reduces to 0.0742. Now, if we go down to a sample of size 80, when we train on that, you're going to see the trees disagree wildly with each other. So there's just constant disagreement among the trees, and as a consequence, the red model, which is the average of all these blue models, the bagged estimate, is actually doing remarkably well. It hardly looks like a step function anymore, and the test set mean squared error is incredible. So 0.066, and we've just knocked off almost 0.01 from the large sample size. Well, you can go too far on this, and so if you were to fit your model on samples of size 20, what happens is you never get splits in these two tails, and the tree doesn't do very well, and the test set mean squared error is very poor. So this is just another example illustrating this concept of destabilizing an estimator will help when you bag, when you average the estimates. Well, this went on for a few years, and the method of destabilizing trees that kind of won was something that Bryman thought of again. So this is the idea of a random forest. And so what a random forest does is when it builds the tree, it only considers a random subset of predictors at any given split. So I believe the first thing Bryman tried was, well, let's just pick one predictor at random. And I think he determined that that didn't work very well. But then he said, let's just reduce the number of predictors that I'm going to consider at any split. And that turned out to work a bit better on the problems that he was studying. And it turns out that this is very smart way to do things. So what Bryman recommends is the following, and this is what's implemented in the R package, is that if you're building a classification tree through various trial and error approaches, there's not a theorem that says this is the best value, but you should choose the square root of p predictors at each split to do your search. Okay, so for example, if I had 100 predictors, then each time I wanted to introduce a split in my tree, I would draw a random sample of 10 predictors and only search those for splits. If you're building a regression tree, the default value is p over 3. So this number of predictors that you're going to search at each split is a parameter that you pass to the random forest function, and it's called mtry. So what I'd like to point out is that if you set mtry equal to p, you get bagging. So you don't need to do what I did a couple slides ago where you write your own for loop and keep track of the results and do the averaging at the end. You would just set mtry equal to p rather than using the default values of the square root of p for classification or p over 3 for regression trees. So there, just as an illustration of this, let's go back to the bike sharing, the Washington, D.C. bike sharing data that we discussed during our the generalized additive models lecture. And so remember, we're trying to predict the count of bicycle rentals as a function of the weather that day and whether it's a holiday, whether it's raining, temperature, and those sorts of things. If we just fitted a linear regression, which is not great, you can see what the residual sums of squares equal. Now let's go throw this into a random forest. So you're going to see the syntax is almost identical to LM with one exception. So we can set mtry equal to the number of predictors. So in this case, I have 11 predictors. Let's just try bagging. And so by default, you're going to see random forest builds 500 trees. And it's going to try 11 variables at each split, indicating we're doing bagging. And here is the mean squared error of our residuals, which is substantially better than what we got with LM. We found a few nonlinearities when we use the GAM, so we know that LM isn't going to find everything. And your R squared jumps up from about 83% to about 88%, just without doing anything. Finally, let's go try a random forest. And so if we fit a random forest, notice I've gotten rid of the mtry option. This is a regression tree since count is a numerical variable. If you want a classification tree, just make count a factor. Don't do that because that has too many levels. But if you had a categorical dependent variable, make it a factor, and then random forest will fit a classification tree instead. So notice we have 11 predictors. If we take 11 divided by 3 and round down, so that's going to be 3.6666 something or other, round down you get 3 predictors. And so every time that the random forest tries to introduce a split, it is only going to search through a random set of 3 variables. And what you'll see is that our mean squared error reduces a bit, and r squared therefore increases, I guess we would say this increases in the second decimal place, or first decimal place. So it's not a large improvement, but you're getting a small improvement by doing random forests instead of bagging. So let me just, we're going to come back and have some discussion of various diagnostics in a minute in the next video, but let me just point out that random forests are the closest thing we have to an almost automatic method where you can just put your data in it and it will do something reasonable to it. You don't need to find transformations. You don't need to deal with outliers, at least on the X side. It's the closest thing we have to a fully automatic method.